So I want to start this example by putting up two different equations that I'd like us to attempt to solve. Let's start on the window side of the room with the equation x squared equals, what's going on here? X squared equals 17x plus 60. So there's one example of a quadratic equation. Let me also give an example for the wall side that we can both tackle. How about x squared minus x is equal to 90. So here are two equations. What I'd like to do just to get us started is to have you solve this equation the way that you know how to solve this equation. So let's have that be the way we start the process, and then we'll regroup and see if there's a different way to approach it. So first of all, I agree with all these solutions. But what I want to draw your attention to is that some of you stopped too soon in your solutions to these problems. As I walked around, what I saw happen for a few of you, just going back to what we were talking about before, is that you did this process on the left, right? You did all the factoring, and you didn't bring it home and figure out what to do with that factoring, right? After you've factored it, yeah, you've accomplished something, but you haven't quite solved for x and found out what value x has until factoring is only useful if you can use it to break apart an equation that has 0 on the other side into two simpler equations and then solve each of those two simpler equations. So maybe one way of thinking about it is that when you're factoring, this 0 over here on the right-hand side of the equation is really a green light. It means go ahead and split these two factors apart from one another. Give each one of those factors its own 0, and then solve the simpler equations that you end up with there. Because a solve for x problem is not done until you've gotten x equals something. In these examples, we have two different x equals 20 and x equals -3 for the example on the left, x equals -9 and x equals 10 for the example on the right. Let's go through the process one more time just to cement sort of how we got these answers. So Nick, let me come back to you on the example from the window side. So what was your process? How did you get down to x equals 20 and x equals -3?
So what I first did is I put everything on one side, so I subtracted 17x, and I subtracted 60, and I added it to the other side. I subtracted to the other side.
Yeah, right. So your top priority in step number 1 is getting everything to one side. Because when we get everything to one side, what's left over on the other side? 0. Again, our big green light here. Having a 0 on one side means that we have a green light to factor. So we want to get that 0. And the way to do it is by subtracting everything from one side to the other. X squared minus 17x minus 60. Okay. So now we have an equation, x squared minus 17x minus 60 is equal to 0. Then what did you do from there?
What I did is I factored it, but I got x minus 20 and x plus 3.
All right. And where did that 20 and that 3 come from?
Because like -20 times 3 equals -60, and
Okay.
-20 plus 3 is -17.
Yeah, that's the sum and the product game. Right? You were looking for two numbers which multiply together to give you the constant term here, the -60. And those same two numbers have to also add together to give you that term in the middle, -17. So you started by thinking about what numbers can I multiply together to get -60. So you ran through some possibilities, 60 and 1, 30 and 2, 20 and 3, 15 and 4, 6 and 10, and then found one of those pairs which when we add them together gave us -17. And so you settled on -20 and +3. That is the winner of the sum and product game. So you used those numbers to construct the factorization, x minus 20, x plus 3. Let me pause for a moment and ask, if you were working on this on a test, how could you know whether or not this was a correct factorization? If you wanted to check your work, what could you do? If you get nothing else out of this class, I want you to get the ability to know that your own answers are correct. So how could you do it here?
Just FOIL that?
Yeah. When in doubt, you can FOIL it back out. Right? If we were to FOIL this back out, we would get x squared plus 3x minus 20x minus 60. And when the plus 3x and the minus 20x combine, because they're like terms, we would get that negative 17x in the middle. So FOIL it back out, and you get exactly what you started with. You can check your own work. That's the greatest thing about factoring, is that you'll know if you did it correctly, if you just take a moment and multiply it back out. Okay, so this was the winner of the sum and product game. And again, this was a place at which I saw a number of you kind of stopping and saying, all right, I factored it, cool, I'm done. There's more work to be done, because we need to know x equals what? What value of x is going to solve this equation? So how did we then go from there to there? What happens next?
I did x, I did x minus 20 equals 0, and then x plus 3 equals 0.
Yes, so that's the zero factor property in action. Right? That's why we insist that the other side of the equation be equal to 0, because if it's not, we can't split this apart in this way. 0 is the only number that has the property that we cannot multiply two things and get that number, 0, unless one of those things was itself equal to that number. We can't multiply two non-zero things and get 0. Therefore, if I multiply x minus 20 by x plus 3 and get 0, that must mean that either x minus 20 was itself equal to 0, or that x plus 3 was itself equal to 0. So that's that zero factor property. This is the most crucial step in the whole process. It's why we care about factoring. If it were not for the zero factor property, factoring wouldn't be very interesting at all. I don't think we'd learn it in a basic algebra class. But because of this step, factoring is really, really useful. It then gives us these two equations which are much more straightforward to solve. How do I solve x minus 20 equals 0? Add 20 to both sides, which gives me the first solution, x equals 20. X plus 3 equals 0. Likewise, solve it by subtracting 3 from both sides. And it gives us the other solution, x equals minus 3. So if we annotate this just with our thought process going along, we kind of did three things. First thing we did was make one side equal to 0, which is super important because without that step, we can't do this important splitting apart step later. Right? So make one side 0. Make that your top priority when trying to solve an equation involving a polynomial inside. So make one side equal to 0. Then the second step was factor. And the whole point of doing that factorization is that then we can split each factor with its own equals 0 using the zero factor property. That's the all-important step. And then once we've applied the zero factor property to split the equation apart into two pieces, we can solve each of the simpler equations. Each simpler equation. And then we're done. So one of the things that differentiates solutions of these kinds of equations from the equations we talked about in the first half of the semester is that these equations can have more than one solution. In fact, we should probably check, right? Anytime you solve an equation, there's a built-in check that you can use. Just try that value back in the original equation and see if it works. So if x is equal to 20, let's go back to the original equation, x squared equals 17x plus 60. If I plug 20 into that equation, then 20 squared is 400. 17 times 20, 340, plus 60, and it works. So 20 is the solution of this equation. Yeah, same thing if we try negative 3. We're going to get different numbers. If I take negative 3 and I square it, I'm going to get 9. 17 times negative 3 is negative 51 plus 60. And sure enough, negative 51 plus 60 is equal to 9. So it's possible for one of these equations to have two different numbers both be solutions to the equation. We didn't talk about this in detail, but let's take this opportunity to point out how we might have known that ahead of time. So is there a way for us to know when we see an equation like x squared equals 17x minus 60, plus 60, sorry. Is there anything about this equation that has the power to tell me how many solutions it can have? Brittany? So the number of solutions that we got to this equation when we solved it a minute ago was that it had two solutions. In fact, if we rearrange this equation to get the 0 on one side, that's probably an advisable thing to do. Let's go back to this version of it. X squared minus 17x minus 60 is equal to 0. So I have an equation with a 0 on one side. And on the other side of the equation is an expression which is a polynomial. What's the degree of this polynomial? So when we first talked about polynomials, we talked about what their degree, how to identify their degree. Yeah. Why is it 2?
Because the exponent is 2.
Yeah. The highest exponent that we see in this polynomial is a 2. It's right there on the x squared. And at the time, it was just sort of a fun thing that we did to classify polynomials. But now that we're talking about solving equations involving polynomials, that degree actually has more meaning than it used to. Why we care about the degree of a polynomial is that it sets a limit on how many solutions of that polynomial equation can have. So a polynomial of degree 2, it can have two solutions. Different solutions. Now it turns out that it doesn't have to have two solutions, but it might, right? It could have two solutions. And in fact, we saw that this example does, right? X equals 20, x equals negative 3. This polynomial could have fewer than two solutions. It could have had one solution, different solution, or it could have no solution at all. But here's what the degree tells us. And this is a fact that is so important that we call it the fundamental theorem of algebra. Does anyone know what the statement of the fundamental theorem of algebra tells us? Anytime a mathematician calls a theorem fundamental, it's pretty important. So that's the prediction. The fundamental theorem of algebra is going to tell us that the number of different solutions a polynomial equation can have is limited by its degree. So if we're solving a polynomial equation that has degree 2, we cannot get any more than two different solutions, but we could get up to two different solutions. If I had a polynomial equation of a different degree, let's say I just go in and I change this example. X to the 4th minus 17x minus 60. So what do you think is going to happen here? How many solutions could this equation have?
4.
It could have 4. It could have 3. Or 0, 1, or 2. But the fundamental theorem of algebra says that that's it. That it can't have any more than 4 solutions if its degree is 4. So just to get the statement, a polynomial of degree, let's call it n. Polynomial of degree n may have no more than n distinct solutions, distinct roots, we'll call them, than n distinct roots. And when I say the word root, because that's a meaningful math word, roots are just places where that polynomial is equal to 0. Right, so that's another place where we want the equals 0 part to be in the discussion. But the fundamental theorem of algebra says that the degree of a polynomial limits the number of different solutions to its equation equals 0 that it can have. So if my polynomial has degree 4, I could have as many as 4 different solutions, but I can't have 5. Right? I can't have 10, but I could have anything 4 or less.